Hi, so we are Team Sicko Bamba Capital Management, and we're here to predict energy prices using deep learning in Smojo. So to begin with, we begin with data pre-processing, where we use linear interpolation to fill missing values. Then we normalize the data and we obtain the persistence baseline loss. Next, we did some feature engineering where we used 12 features, which were the mean standard deviation difference and skewness of the x values at different time periods, which were t minus 25, t minus 75, t minus 100, and t0. So this means that our window was from t0 to t minus 100 hours, and we use this to predict for t plus 5 hours or 5 hours into the future. Yeah, so just a bit on our neural network. We use a size of 128, a solver type of Adam, input size of 30, 10,000 iterations, and 5 repeats. So this yielded a test loss of 0.019 for our neural network. So here's our test loss graph, where you can see that initially from the start, there was a bit of deviance between training and test losses. But until around 695 iterations, we suspect the model started to undergo memorization, as it can be seen that both test and train have plateaued. Okay, now Gabriel will explain further.
Okay, so for neural network, looking from the graph, there's training predictions and the test predictions. So the actual and predicted values follow the same trend of values, which means that there's a good accuracy and present in our model. However, as you can be seen, the model is not exactly perfectly accurate, as the predicted energy is still lower than the actual energy, as you can see by the deviation between the actual and prediction, and for both of the graph. Next. And for the neural network, it can be seen when we do a correlation between the actual versus training predictions and the actual versus test predictions. From the graph, it can be seen that both are actually very highly correlated, as it can be seen from the positive linear relationship. However, the actual versus test prediction showed a stronger correlation. However, it is less correlated as compared to the actual versus training prediction, as the greater dispersal of the points in the graph is because of the noise accumulated from the test losses during the training. Yeah, next. And for our neural networks, we have this graph of the lag correlation. And based on our understanding, there's a lag of 0, which means that the effect of the variable x on a target y is instantaneous. Next. And so based on our evaluation, it can be seen that we have an initial persistent loss of 0.1162 as compared to our test loss of 0.0193. So this means that our model is good, as the test loss is significantly lower than our initial persistent loss. So it is a good model because it beats the benchmarking based on the changes of our features by increasing the pass window to t minus 100 hours to get a better result, and increasing the number of repeats to improve our persistence loss. So thank you, and hope you enjoy our presentation.
Thanks.